Before we can move on to algorithms for our Steiner tree and the restricted metric Steiner tree problem, we need some theory. We want to define what is an approximation preserving reduction. Intuitively, approximation preserving reduction is a reduction from one problem to another one, where if you find an approximation algorithm for the second problem, then it gives you the same approximation factor for the first one. How do we do this? Let's say we have two minimization problems, pi1 and pi2. Later, we will have the example where we have Steiner tree and metric Steiner tree. So one of them is Steiner tree, the other one is metric Steiner tree. We will map out the reduction that we're trying to achieve down here. Now, formally, an approximation preserving reduction from problem pi1 to problem pi2 is a tuple f and g. And these are polynomial time computable functions. And they have two very important properties. The first one is that for every instance I1 that we can find of problem pi1, so we have some instance here, the function f computes as an instance I2 of the second problem. So if we apply the function f to this instance, then we get an instance to the second problem. And there we also have the additional property that if we can find the optimum for this second instance, then it is as large as the optimum for this first instance. This is something important we need. So we take this instance, we create another instance where the optimum can only get smaller. What about the second function, g? If we have some feasible solution t for this instance, or let's say we have computed some solution, not necessarily the optimum, but something feasible, then with the function g, we can find a solution for the first problem. So we can find a solution S by computing the function g of this instance I1 and the solution for I2. And for this solution, we get the important property that the objective value of this solution is as large as the objective value of the solution t. So we reduce from an instance of problem 1 to an instance of problem 2, where the optimum can only get smaller. And then we take a solution from problem 2 and we move to a solution of problem 1, where the objective function again only gets smaller. And these are the important steps. Whatever we do, we cannot get something where our optimum or our solution value gets larger. So every step we do in this reduction only makes something smaller. So with this, we can find a solution to our instance I1 by calculating function f, finding some valid solution, and then calculating function g. So let's assume that for some two problems, we have found some functions f and g that have these properties. So we have our two problems, and we have an approximation preserving reduction f and g. And now for this problem pi2, we also know that there is some approximation algorithm, and that approximation algorithm has factor alpha. Then this directly gives us an approximation algorithm for pi1, which also has factor alpha. So if we know how to solve this problem within factor alpha, then we also know how to solve this problem within factor alpha. Before we apply this theory, we first want to prove this theorem, which is quite simple. We start with some factor alpha approximation algorithm for our problem pi2. Let's call it A. And now we take any instance I1 of our problem pi1. Now we want to compute the instance I2, the solution t, and the solution s. Can you do that? The instance I2 we get by applying the function f to I1. So I2 is f of I1. The solution t for I2 we get from this algorithm. So t is a of I2. And the solution s of I1 we get by the function g. So this is g of I1 and t. And as I told you before, every step we do in this way only makes what we get smaller. So if we look at the objective function of the solution that we create for our instance I1, This is only smaller but not larger than the objective function of the solution t we got for I2. And for A, we know it's an alpha approximation, so this is at most alpha times the optimum for this instance. And the property for F tells us that the optimum of I2 is at most as large as the optimum of I1. So this is again at most alpha times the optimum of I1. And now we directly have our inequality here. The objective function of our solution S is at most alpha times the optimum for our instance.